So now we are going to talk about extremal problems. So we have seen some examples of extremal problems before. What are the extremal problems? Essentially, this is about the relations between more of a quantitative relation between graph parameter and structure. Or you can consider it as an extremal behavior of graph. So both of them are, essentially the same thing. And you can also consider it as this is about inequality. The example we have seen is that if the minimum degree is at least k, then we have there is a cycle of length at least k plus 1. So this is what quantitative relation between the minimum degree and the length of cycles. And also this is the extremal behavior of the graph with the minimum degree at least k. Among them, what's the extremal behavior? What if your graph has as small as possible length of cycle, as small as possible curve, and how small it can be? That's this. And this is also about the inequality, right? And also other examples are that the Dirac theorem. So this is, essentially a similar thing. Again, this is the relationship between graph parameters and structure, or it could be relation between several graph parameters. And also this is the extremal behavior of the graph, right? And also the inequality. So those are how we describe the extremal problem. And the study about those are the extremal graph theory. Then what are the, most basic and natural parameter of the graph? One of them is the number of edges. And we want to explore the relationship between number of edges and existence of such a subgraph. So let's say you take a simple case of triangle. And what do you know? If we have number of edges 0, then surely there is no triangle. This is an empty graph. And if your n vertex graph has as many edges as possible, then if n is bigger than 3, then there are many triangles. So we can consider the graph in between. So these two are trivial. So this means that if you start from empty graph and then you add edges, and then you keep adding edges, then in the end you end up with a complete graph. That means at some point a triangle appears. And natural question is, when does it appear? If you want to make it appear as early as possible, then you only need 3 edges. You add edge, and you form a triangle, you're done. So that's a boring question. So what if you want to postpone the appearance of triangle as much as possible? How much can you push to the later? So this is essentially asking the relationship between these two. And the question is, what's the maximum number of edges in an n vertex triangle polygon? Okay. In order to study about this kind of question, what should we do first? We should try to find the candidates which achieve this maximum number. So how can you come up with an example of graph which has lots of edges but no triangle? One of the graphs that has no triangles are bipartite graph. And then among the bipartite graph, if you try to not maximize the number of edges, you take the complete bipartite graph, and then because the number of vertices is fixed, you make them as even as possible. Then this has the more edges. I mean, this has the maximum number of edges in all n vertex bipartite graph. And this has what? N square over 4, floor of n square over 4 edges. And it has no triangle. Triangle has chromatic number 3, so it is not bipartite graph. It's not a subgraph of bipartite graph. So this shows that this answer is at least n square over 4. This example shows that the lower bar. But indeed, equality holds. This answer is exactly this. And we will learn about this. So to facilitate our discussion, we define this function. We write the ex of nf as the extremal number of f with the maximum number of edges in an m vertex graph which does not contain f as a subgraph. And this is called the extremal number. Or the Turan number. Of the graph f. So technically this is a function. So for fixed f, this is a function on n. However, we just call it the extremal number, the Turan number, but they are actually a function. And let's define this capital T sub r of n be the balanced, complete R-partite graph. On n vertices. So this balanced complete bipartite graph is T2 of n. And we call it the Turan graph. And the small t sub r of n be the number of edges in this Turan graph. So in t sub 2 of n is floor of n square over 4. Okay, so now our study is about this function. Can you find the value of this function? So that would answer the question of this. Instead of triangle, we consider some other graph. Then that graph is F, then this gives us the answer to that question. So what's our fourth theorem? The fourth theorem is about the above question when your graph F is complete graph. So this is theorem by Turan that any case of r plus 1 free n vertex graph that must contain and most is T sub r n edges, and the equality holds only for this Turan graph. Okay, so we want to prove this. And for this, I mean, if you have this G, which is K alpha sub plus 1 free graph, then what happens if you take the complement? Complement saying that it does not have a clique of this size. In its complement, it has no independent set of size r plus 1. So any independent set has size smaller than r plus 1 in this complement. So having this many, this subgraph, which is complete graph, translate into the statement about independent set in its complement. And if number of edges is at least m, then in its complement, its number of edges is 30. So let's say at most 10. And this is at least n choose 2 minus m. So you have this relationship between G and G complement. And then by taking G complement, the following theorem by Caro and Wei implies the Turan theorem. And then n and r be natural number with n being bigger than r. And let's say n is qr plus k, with this k being smaller than r. And any m vertex graph G with the number of edges smaller than k times q plus 1 choose 2 plus r minus k times q choose 2 satisfies its independence number is bigger than r plus 1. It must contain an independent set of size r plus 1. So we consider this. Okay, assume this is proved. We want to show that it implies the first part of Turan theorem. So equality we will discuss later, but this we can ensure. So this, if you take the contrapositive, what do we have? If your graph has more than this many edges, then you have a subgraph of k sub r plus 1. And then if you take a complement of G, then what do you have? G has more than this many edges, then its complement has less than n choose 2 minus this many edges, implies what? And the conclusion is that the complement has a k sub r plus 1. That means it has independent set of size r plus 1. Yeah, so what's this number? So this TR is the exactly number of edges in this balanced complete bipartite graph. And then its complement is exactly the disjoint union of cliques, so that all the cliques have as equal size as possible. It's either one side or, some size of Q or size of Q plus 1 for certain Q. So that's exactly the number of edges here. So this is what? You take a k copies of k sub q plus 1, and then r minus k copies of k sub q. And number of edges is exactly this. So you can check that this is actually equivalent to this statement when you consider the complement. So we want to prove this. Yeah, and the Turan theorem has many proofs, but we want to consider its complement because it's more convenient when we do the following proof, which uses probabilistic method. So let m be the number of edges in here. What we do is we choose an ordering of vertices. Say this ordering is sigma p1 to pn of the vertices of G, which is chosen uniformly at random. In other words, there are n factorial different choices of this permutation, and you choose one of them with a probability 1 over n factorial. And in this ordering, so this is a probability space, and we consider the following random variable. We choose the set, say, u sub u of this sigma of all vertices which comes before or their neighbor. So if you have a graph looks this way, and this is your ordering, then what? This vertex comes before all of this its neighbor, which in U, but this one does not. It has a neighbor which comes before. This one, it has neighbors which come before. This has neighbor which comes before. This has neighbor which comes before. So you only consider this one vertex. But let's say you don't have this edge, then this is also chosen because all of its neighbors are after it in this order. Okay, that's a well-defined set for given this sigma. Then it's easy to check that this U sigma is an independent set in this tree. So this is a one way of choosing some independent set in a random way. And this random is not uniformly random, but there is certain distribution over this random set. I mean, it is independent set. Why this is independent set? If you have U sigma, there is two vertex and then you have an edge between, and one of them must come before the other in this ordering. And the later one cannot be in U because it has a neighbor which is coming before it. So there cannot be any edges inside of this. So let X be the random variable so that it's the size of this U, the number of vertices in U. So this is a random variable whose image is, whose range is a real number, more of a, this is discrete random variable. This value is non-negative integer. Then we can compute this expectation. And for computing its expectation, the most basic way is to write it as a sum of this indicator random variable, where this IV, that depending on this sigma, is either 0 or 1. If this V is in U sigma, it's 1. Otherwise, it's 0. And what? Now, what's the probability that this is 1? Since if sigma is chosen uniformly at random, and when does it become 1? You have V and its neighbor. Let's say U1, U2, U3, U4. Out of this 5, if V comes before the other 4, then this is 1. What's the probability of such thing? Because this is chosen uniformly at random, it's equally likely that one comes before the other comes before. So if you restrict this permutation on here, there are 5 factorial ways of relative position, I mean relative ordering on these 5 vertices. So the probability that it comes before all of them is 1 over 5. So the probability that if V appears before all its neighbor is what? That's 1 over the degree of b plus 1. So degree is the number of neighbors, and then step out of these, you end up having the b for everyone. Then what? The expectation of x is by linearity of expectation. You add the expectation of this IV for all vertex, and that's simply the summation of the 1 over degree plus 1. Okay, and we have the harmonic sum over this number. But what we know is that the summation of this number, if you just sum this number, we know what we have. This is by handshake lemma, 2 times the number of edges plus the n. So this 1 is added n times. So this is fixed. So there are numbers whose sum is fixed. And then you flip it. You take the reciprocal of them, and then you sum. You take the harmonic sum. Then what do you know? Then the summation of this is minimized if this degree, because their sum is fixed, degree of vertices in BG are as even as possible, then this is minimized. But what do you know? If M is what? Smaller than or equal to 2 times what? K times Q plus 1 choose 2 plus R minus K times choose 2 plus N. And because N is Q R plus K, you can rewrite this as R minus K times Q plus K times Q plus 1 times Q plus 1. And this sums to N. So this is a sum of R minus K Q terms of Q, and then K Q plus 1 terms of Q plus 1, then total N. So what does it say? Actually, this is strict equality because we have this strict equality. So from that, what we know? This is minimized when they are as equal as possible. And then this total sum is this. So, and we don't allow non-integer, so everything is integer. Then we have inequality here. So this is bigger than this many terms of 1 over Q and this many terms of 1 over Q plus 1. So that's strictly more than, this number is strictly more than this. So this many terms of Q, each of them, you flip it, you get this. So this is the sum of degree plus 1. And you have this many terms of Q plus 1. So for that, you flip it and you get this. Okay, and then what's this? This is what? R minus K plus K is R. So what did we get? The expectation is bigger than R. Then what do we know? So there exists an ordering such that X is bigger than R, meaning that this U of sigma has size bigger than r plus 1. So alpha of G, alpha contains independence of size r plus 1, as we wanted to prove. So this proves the first part. Then in order to prove the equality case, we analyze the proof of this. Then we can show that. So again, same setup. You have n r, n is qk plus r with this. And if G is an n vertex graph with equality. So before this was strictly inequality, but now you have equality. And let's say alpha of G is R. Then is disjoint union, the k copies of k sub q plus 1 and r minus k copies of k sub q of complete graph. So again, if this is true, then you take the complement, then it exactly implies this part. Because disjoint union of complete graph, its complements are the Turan graph. Okay, what do we do? From the previous proof, you repeat it, then what you get? You get the expectation as the 1 over degree plus 1 now. And you do the exactly same thing, but now instead of inequality, strict inequality, you have an inequality with the inequality being possible. So now you have this. On the other hand, we know that the G has independence number R, so it doesn't have a independence of size bigger than R. We must have this expectation being at most R. So that means this is actually equality. Okay. And what? This equality implies that the degrees of vertices, they are actually must be as close as possible. Meaning that the exactly, this many copies of Q and this many copies of Q plus 1. Yeah, so it's either Q, all the degrees are Q or Q plus 1, and then that many vertices of degree Q, that many vertices of degree Q plus 1. Moreover, what do we know? X must be a constant random variable. So its expectation is R, exactly R. So in other words, average of the number is R. And this showing that there are no cases that X has a value bigger than R. But what if there is one case that the value is strictly smaller than R? Then your expectation is actually strictly smaller than R. Right? All the numbers here are at most R. And there is a number which is strictly smaller than R, and its average is strictly smaller than R. But since that's not the case, there must be a there must be no such case, meaning that all the values for all this sigma is exactly R, which is constant. And from this, we want to show that G is a disjoint union of clique. Suppose that G is not a union of clique. Then there will be three vertex X and Y and G, such that XY and XG are edges, but YG is not an edge. And what we do, we consider ordering sigma, which starts with X, Y, Z, and then later, you arbitrarily write it, and then here you write Y, G, X, then write it, and then these two parts are identical. So only difference is this 3 at the beginning. Then, what? We claim that this U of sigma and U of sigma prime are the same, except X is in U sigma, and Y and G are not in U sigma, and Y and G are in U sigma prime, but X is not in U sigma prime. It's easy to check. For other vertices, whether it's in U or not, only thing matters is that the set of vertices coming before and the set of vertices coming after. For this, as a set of vertices coming before, they are identical, and as a set of vertices coming after, they are identical. So if their neighbors are all in later, this is still all in later. If their neighbors, they have an earlier neighbor, it also have an earlier neighbor. So all of these vertices, they are saying if one belongs to U of sigma, the other one also belongs to U of sigma prime, and vice versa. But the before is different. Then what? X, which is the side of this U sigma, is not constant. A contradiction for this assumption. Thus, G is union of clique. And as we mentioned, their degrees, their vertex degrees, are as even as possible. We prove the proposition as we want. So this is exactly the case where this is disjoint union of clique, and then their degrees are as close as possible. And that proves the second part of the Turan theorem. Okay, so we have shown this Turan theorem. We define this extreme number, and then we determine this extreme number for all cliques. And next natural question is, what if our graph is not clique? So in next video, we will prove a theorem which gives asymptotic value of this extremal function, extremal number, for other graphs. Okay, thank you for listening. I will see you in next video.